Hello and thank you for watching. In this video we're going to go through the vector product examples and their consequences. Okay, so to start off I'm going to make a quick proposal and claim that if we take the magnitude of the cross product of two vectors, this is equal to the product of the magnitudes times sine theta. And you could just believe me that this is true, but you could also try to prove this for yourself. Although I'm quickly going to say that, okay, this looks very, very similar to the dot product, because with the dot product we just had the sine theta replaced with cosine theta, so maybe we can get some, link them together in some way. So if we square this, we get sine squared theta. And now I'm thinking, okay, well, sine theta plus sine squared theta plus cosine squared theta is equal to 1. So we get that this times 1 minus cosine squared theta is equal to the magnitude of the cross product squared. And so we have this being equal to, well, v dot w squared, because if we recall that this is equal to vw cosine theta. If we recall this, then we have that multiplying those together and our cosine. If we square all of this, we get the magnitude of v times the magnitude of w times cosine squared theta, or cosine theta squared, which is just these multiplied together. Okay, so now you might be thinking, okay, why is this useful? Because surely if we have this cross product, we get a vector output. So what does this magnitude of the cross product actually tell us? It's not the same as the scalar product, which has multiple uses. Well, now I'm thinking, okay, it gives us a vector. Maybe that's a good thing, because say we have a triangle of side lengths A, B, and an angle of theta here, right? So obviously we can find the angle, or find the area of this triangle, by just saying, okay, well, the area of this triangle is just half of AB sine theta. Okay, but what if we don't know the side lengths, or we don't know the angle between them? Of course, say we're given like two vectors. Say we're given a vector v equals v1, v2, v3, and now we're looking in 3 dimensions already, and a vector w, w1, w2, w3. Or, of course, we can always split this triangle into, more, into something simpler when we just have like these vectors, but we're only given 2 vectors. So of course we need to find this, and we need to find this, and then we need to find the angle between them, so we have half of this. This is the area of the triangle if we have some vectors instead of our AB, and of course this is simple. I mean, if we didn't have this angle between them, this would just be a straightforward calculation, but then we need to work towards finding this angle between them, and this would be long and tedious, because we'd have to be like, okay, we have this, we need to split this up into components, and then we need to find this angle. But instead we've got this shortcut method of using the cross product. So okay, we know that this is just a cross product, so we know that this area of a triangle if I can write, that is, triangle is half of our v times our w. And I guess this makes sense. The reason why I didn't go into proving this is because it's not a very difficult proof, but it's quite a long and tedious proof. the viewer, this will be left as an exercise for the viewer at the end if they wish to do it. Okay, moving on. Okay, this area of the triangle is half of the magnitude of v times w. So what if we think about a parallelogram this time, and say we're just given our vector here and our vector here, because these are just identical but they're shifted from these, so we only care about their direction, we don't care about their actual position. So okay, how do we find the area of this? Well, okay, if we notice that if we split it into two triangles, these triangles are exactly the same, and okay, you know, we have some angle here, so the area of this parallelogram is just 2 times half of magnitude of v times w, and so this is just equal to v times w. So that's great, you know, we have a shortcut for finding the area of a parallelogram given just 2 vectors. And that's all I want to cover for this video, because I don't want to go too far. I don't want to overstep. We can also use this cross product or cross vector product to find some volumes. We can use it to find equations of planes. We can use it to do many other things, but I want to leave those for separate videos. So I'll just give a quick example of using this to find areas. So let's say we have a parallelogram with which has the vectors v equals let's say 1, 3, 5, and we have another vector which goes 7, 1, 1, for example. And let's say these make a parallelogram. Let's say like we just have like two vectors of some sort. We don't actually, as long as they're not collinear, it's fine. As long as they don't form a straight line, we're fine, because we will just match those other 2 vectors in and translate them to form a parallelogram. Let's say we want to find the area of the parallelogram made by these 2 vectors, then it's obviously just the magnitude of the cross product. So we'll have, okay, our 1, 3, 3 here multiplied by our 7, 1, 1, and this is equal to, okay, 3 minus 3, 0, and then we have 21 minus 1, 20, and then we have 1 minus 21 minus 20. So this is just 20 squared. The magnitude of this is just 20 squared plus 20 squared, which is 20 root 2 is the area, which is nice. Okay, and one final thing I'd like to mention. I talked about collinearity. I said that as long as they're not in a straight line, this is fine. I will quickly go back to this here. So if the theta is 0, then we have that this cross product is also 0. The magnitude of this cross product is also 0. So this is helpful, because we're implying this relationship that if we have this equal to 0, then it implies that angle between them, and the angle between them is also 0. So I suppose this makes sense, because let's say we're given 2 vectors, right, and we want to find a normal vector to both of them, then that's just a cross product, you know. So we'll have like something going through both of them that makes them, that's orthogonal to both. But now say we have vectors pointing in the same direction, then we can find however many vectors we want that are orthogonal to these 2 vectors, because they're pointing in the same direction. You know, we can just rotate we can just get an orthogonal vector, and then just keep rotating it around, and we'll get as many orthogonal vectors as we want. And so this definition applies. That's all. Thanks for watching. Bye bye.